This is a step-by-step guide on how to run Bayesian regression in JASP. So we start with the dataset, which contains 103 participants. This comes from my research with chess players, in which I was investigating how they acquire their expertise. There are loads of variables that for this video we are going to use only 3 of them. National rating, which is the dependent variable and measures their chess skill, and this is the total amount of hours of individual practice and total accumulated hours, in both cases actually, of group practice. So I created 2 variables that we are not going to use, and you don't have to create these variables, but I want to show you the descriptive statistics for illustration purposes. So these 2 variables are the mean centered, total individual practice and total group practice. So basically what I did is from each value of individual practice, in this case, I've subtracted the mean of that variable. And the same with group practice. I subtracted the mean from each value of group practice. Now what happens with this new variable? Well, if for example you had the mean of group practice is 7,921.061 hours. So if your amount of practice is 0, then your new value, or the value in this new variable, would be negative 7,921.061. If your amount of practice was actually the mean, then your new value will be 0 because you're subtracting the mean. And if your practice was, let's say, 17,921, then your new value would be 10,000 because it's 10,000 more than the mean. So in this mean center, we've got negative values. That means that the score is lower than the mean. The mean is 0. And then positive values, that means that the score is larger than the mean. So what it does is to create a variable in which the mean is 0, both independent variables, and that will change the intercept of the regression. And I'm going to show you when we do the analysis. So let's start with descriptives. So we go to descriptives here, and then we've got national rating. We've got total individual practice, total group practice. So we've got the mean national rating is 1990.5, a standard deviation of 222.6, individual practice 5,404.2, and a standard deviation, very large standard deviations, 5,814.9. On group practice, the mean is 7,921.06 and the standard deviation 6,827.4. Okay, so these are the descriptives, and we need some plots there. And for the plots, we may have to change the order there. Let's see. So we are going to do scatter plots. We want to have national rating on the y-axis and the other 2 variables on the x-axis. So what is doing here is putting national rating on the x-axis. So in order to change that, we put national rating on the bottom of the list. And now we've got national rating with individual practice, national rating with group practice, and this one is group practice and individual practice, but the most important are these. So we need to do some changes. We don't want this smooth line. We prefer a regression line or nothing. So if we do add regression line, we put linear, because we are using linear models. So this is that. Now we here you can use this thing on the right, at the bottom right corner, to increase the size. If you need, you can use this arrow to get more space, and this. So here, note that the x-axis have a scientific notation. So we've got this E plus, and the number there indicates the number of zeros that you have to add. So in this case it's 0.0 plus 0, so this is 0, that's the value 0, and then we've got 5.0 plus 0.3, so that means that you need to add 3 zeros. That means that this is 500, and this one is 1 and 4 zeros. This is 1000, 1500, 2000, 2500. And this is the distribution of the individual practice and national rating. This is the distribution, and these are the values. The gray area is the 95% confidence interval of the estimation of this line. But we are going to get rid of that. So we just get rid of that by ticking there. So we've got the regression line, but we may not need the regression line, and we put like this. Okay. Now you can copy this. So if you increase the size, dragging. This is not good. It adjusts itself, and then you can do this. You can tick there, and then copy and paste, or save it as an image, and then you paste it in your document. Okay, so let's now go to the Bayesian analysis. So before we do that, I show you the descriptives of the mean center. So you are going to see that the standard deviations will be the same, but the mean will be different. Okay, so we press this arrow so we get all the results here. So you can see that for individual practice, we've got 5,404, total group practice 7,921, and in the mean center, the equivalent mean center, it's 0. This 0.002 and minus 0.03, this is because of rounding. So because the mean is up to 3 decimals we use, but could have used more decimals, and this would be 0. But you can see that the standard deviation is the same. Total individual practice 5,814.9, and the same here, and these are the same. Note also that the national rating is the descriptives are over all the participants, 103, because we've got national rating of all the participants, but we don't have individual and group practice from all the participants. There are 14 missing values, so the means will be calculated over less number of participants. Okay, so now we go to the regression analysis and Bayesian linear regression. Okay, so for Bayesian linear regression, we are not going to use the mean center variables, but why did I show you this? It's because JASP does this automatically when it does the analysis of Bayesian linear regression. Then it will transform the independent variables into mean-centered, and that's the way the coefficients of the linear regression will change accordingly. So it doesn't change the beta 1s, the beta 2s, but it changes the beta 0. And I will show you what that value will be. So dependent variables, national rating, and covariates are individual practice and group practice. Okay, so and we get immediately the table with all the analysis. Now, first important thing, we've got here the 4 models. This is the model that includes only the group practice variable. This model is individual practice and group practice, and then the individual practice only, and then the null model, so the model that doesn't include any of the independent variables. Why are they ordered this way? They are based on this BFM, which, so the best model is the group, the second one is in both variables, third one individual, and the fourth is the null model. So that's why it follows this order. Now, this PM here is the probability of the model before observing the data. So this is the prior probabilities we give to the models. And the default prior, it's interesting because it gives twice as probability to the combination of two variables than to the individual ones. We don't want to do that. So we want a uniform distribution in which all the models have the same prior probability. We do that by going to advanced options. And advanced options here, it gives us this JZS is the Jeffrey-Zellner-CO prior, and that's the prior for the parameters. And this one is the prior for the models. And it's using a beta binomial 1, 1. I'm not going to explain this, but we tick in uniform. And you can see that now probability of model changed to 0.25 in all of them. So it's a uniform distribution. We give 25% or 0.25 probability for to each of these models. Okay, so things to take into account here are these two things. Base factor, do we want base factor 1, 0 or base factor 0, 1? We can also use the log, but we are not going to use that here. And whether we compare to the best model or we compare to the null model. So I'm going to go through that in a minute. But let's see these things here. Posterior summary. So this will be the posterior distribution of the parameter values. Okay. So the interesting thing is well, we've got 4 models, and the 4 models will have different estimations of the parameters. Like for example, null model beta 1 will be 0 and beta 2 will be 0. So that's the estimation. Now for individual, then beta 1 will be 0, but beta 2 will be some value more than 0. For group, beta 1 will be more than 0 and beta 2 will be 0. And for the combination, the model with the two variables, both beta 1 and beta 2 will have some value that is different than 0. So they have different estimations. So when we do the posterior distribution of the parameters, which model are we going to use? One alternative is to use one model, each model separately. But JASP has the philosophy that we need to combine the 4 models. How do we combine them? Well, based on their posterior. So the posterior distribution gives that. So we start with 0.25 for the 4 models, and then we go to a posterior distribution, which is the probability of the model after observing the data, and it gives us a probability of 0.66 to group, 0.329 to both variables, 0.008 to individual, and almost 0, very, very small number for the null model. So basically, we are going to use for each of the parameter, the estimation of the parameters, the total group model will have 66% of weighting on that estimation, and the total plus group, sorry, the individual plus group will have a 33% weighting, and the individual is 0.8 and null model negligible. So that is it combines the 4 models to make the estimation of the parameters, and that's what we get. So we get that the intercept is 1988, and that is the mean of national rating. Now, you may think that this is not exactly the mean that we reported before, but the mean we reported before was over 103 participants. But in this case, because for the regression analysis, we use only 89, so the descriptives will be different. So I tick here in descriptives, and then we see the descriptives. So you see that now it's over 89, not over 103. So this the total individual and total group don't change because it's the same as before, but national rating changes because now it's calculated over 89, not over the 103 participants. So this is the mean 1987.56, standard deviation 208. If you see the intercept is the mean. Okay, exactly 1987.5618, which is exactly the mean. That is what changes by using the mean-centered independent variables. Now the beta 0 in all the models is the same. So in the null model, the beta 0 is the mean. But in the other models, if we use the traditional approach, non-mean centered independent variables, then the beta 0 changes. But here, because we use mean centered variables, then the beta 0 will be exactly the same in the 4 models. Okay, and then we've got an estimation for the beta 1 group is beta 1, 0.0142, and beta 2 individual practice 0.021. So that's the estimation. Okay, so we now go to this table of the Bayesian linear regression. So that tells us about the prior, the posterior over the models, and the base factor. Okay, so if we do base factor 1, 0, and in each row it will compare. The base factor will be in the numerator. We use the probability, the posterior probability of that model, and in the denominator, the posterior probability of the null model. If we do base factor 0, 1, in each of the rows, the null model, the posterior probability of the null model will be on top, and on the denominator we've got the probability of the model in this row, in the row that we have the value. And the other thing to take into account is, are we comparing to the best model or compared to the null model? So the base factor here is comparing versus the best model, not against the null. So if we put compare to null, now it applies what I said before. In each of the rows we've got, so this is BF01 and compared to null. So the 0 model is the null and the 1 model is the model in the row. So here we are comparing null versus null, and of course it's 1. Here we are comparing total group with null, and we've got the null on the numerator on top, and group on the denominator on the bottom. And here again, null versus the two variables group, and again here null versus individual. So we can see that null is much worse than the others because it has a base factor that is below 1. But you can see that in the posterior for the model, that is much lower in null than all the others. Okay, so if we put BF10 again, now we get in BF10 we've got the model in this row versus the null model. So again, null model versus null model should be 1. Then this is group model versus null model, and we've got 137,759, and the both variables model, two variables model versus null model 68,000 and something, and individual practice only 1,724. So all the models show that are much better than the null model. Okay, so we've got here the probability of the model before observing the data. That's the prior probability of the models, which we use a uniform distribution. And then we observe the posterior probability of the model after observing the data. So almost 0 for null model, 0.662 for group, 0.3296 for the individual plus group, and then individual 0.0083. Now these four values must add to 1, like these four. So that's an elegant thing of the distributions. The prior distribution adds to 1, the posterior distribution adds to 1. So basically what happens is a redistribution of that probability when we go from prior, before observing the data, to posterior after observing the data. So I'm going to return to compare to best model. So basically in compare to best model, now the base factor 1, 0, and the 1 is the model in the row, and the 0 is the best model. So total group is the best model, so compared to itself is then the base factor will be 1. Now when we compare the model with two variables versus the best model, which is the group, then the base factor is 0.5. When we compare individual versus group, 0.0125, and when we compare the model versus group, it's a small value. We can do the same, but 0.1, BF01. So when we have compared to best and BF01, basically what we are comparing here is the best model over the model in the row. So here, best model versus best model should be 1, Best model versus the model with the two variables is a Bayes factor of 2. So not very strong evidence very almost anecdotal evidence in favor of the model with two variables over the model with only group. Sorry, the model of group over the model with the two variables. But if we need to decide which one we keep, so these are the best two models. The model with group only, which is the best, and the model with two variables, total group and total individual. So the evidence is a little bit in favor of group only, but it's not a strong evidence. Not even, it's just anecdotal. So what do we do? Well, if we don't have to decide, we don't do anything. We just provide that evidence. We say that the Bayes factor is 2 in favor of the model with the group variable over the model with the two variables. If we have to decide, I would choose the model with less variables. But as I said, if we don't have to decide, we just report the evidence. And most cases, we don't have to make it in any decision. We have to report the evidence, and that's our job as researchers. Then it will be the jobs of policymakers or engineers or practitioners to make decisions based on the information we provide. Okay, so in this one, BF01, when we do compare to best, this is the best model versus the individual, so group versus individual, a Bayes factor of almost 80, so very, very strong evidence. And then the best versus null is the model of the group with the group variable over the null model it has a Bayes factor of 137,759. So decisive evidence in favor of the group model. Finally, what's BFM? BFM compares the posterior odds versus the prior odds of the model in the row versus all the other models. So here what are the posterior odds for the group model? Well, we calculate the posterior probability of the model versus the posterior probability of the sum of the other models. So we know that these four probabilities need to add to 1. So if this probability is 0.6621, then the probability of the rest is 0.3379. So when we obtain the ratio of these two probabilities, then that's 1.959, or let's say 1.96. And then that's the posterior odd, and then we get the prior odd, which is 0.25 versus the rest, and the sum of the rest is 0.75. So when we do 0.25 divided by 0.75, that's 0.33333. So we need to obtain the ratio of these two odds. So the posterior odd for model group versus the prior odd for model group, and we get the BFM 5.8785. So BFM is a comparison of this model versus all the other models, and obviously the best one, it has a better Bayes factor, which is 5.5 times better than the combination of all the other models. Total individual to total group is 1.47 versus the combination of the other models, but individual and null, it's it's much worse than the rest of the other models. Just to finalize this video, when we've got the summary, the posterior summary, we've got these are the estimates for the intercept and the two slopes. So this is beta 0, this is beta 1, this is beta 2, or the other way around, depending on how you defined in your model. So this group, usually I use it as beta 1 and individuals as beta 2. For the report purposes, you don't have to worry about this or this. I'm interested in the 95% confidence interval. So this is the confidence interval for the intercept, which again is not very interesting, but this one for the two betas, yeah, this goes from 0 to 0.112, and in this case from 0.0078 to 0.0212. And that's what you need to report regarding the parameters, the base factor 1, 0, and the probabilities, the prior probabilities and the posterior probabilities are the ones you have to report. So probability base factor 1, 0, you put here, and you report these values. Not these values, we compare to null. So these are the base factors 1, 0 comparing to null. So if the comparison to null is a value less than 1, which obviously is not the case here, then you use the BF01. So you report the BF10, but then in the text, when you have to describe what happens, then you need to return to BF01, and you interpret as the null model being better than the other model.